We are at a very exciting point in the syllabus here. We are finally moving from classical physics to modern physics. This is the beginning of quantum. And we're coming back to blackbody radiation. So you might remember from a previous video that I said that stars are a thing called a black body when, depending on what their temperature is, they can release different wavelengths of light. Okay, and here we've got a diagram similar to the one I showed you before, 3000 degrees Kelvin, 4000, 5000. And for each of those, it tells you what wavelengths they emit and what intensity they emit them all. And each of these emit almost every wavelength of energy. It's just the intensities that are different. So lower intensity for lower temperatures, but also the peak wavelength is around the red light spectrum, maybe at about 700 nanometers, whereas for a hotter object, the peak wavelength shifts further to the lower wavelengths. Maybe this peak wavelength here is about 500-600 nanometers, more of a bluish greenish light. Okay, so what do we have to do? We have to analyze the experimental evidence about blackbody radiation, and we've got to talk about two people. We've got to talk about Wien and Wien's law, and we've got to talk about Planck and what he did to the model of light afterwards. We've got an equation here, but I am going to throw in another equation as well, um, which is E equals HF, which is very important. Okay, so experimental evidence about blackbody radiation. Now, I told you that stars are black bodies, but they're not the easiest thing to analyze because they're very far away. It's hard to confirm what their temperatures are and that sort of thing. So we created our own artificial black bodies. What you do is you get a box made out of carbon of some kind. It could be made out of graphite or soot or something like that. We have a box that's got a very narrow opening, and we use that opening to determine the temperature. So we determine the temperature by looking at the light. We have some kind of camera or device that sees out there. Inside the box, we have the object we want to measure. It could be just a chunk of metal, and that metal is very hot, so it's been heated up to a certain temperature. Since it's red, you could probably guess what temperature it might be, around that 3000 degrees Kelvin possibly. Actually, no, it'd be much less than 3000 degrees Kelvin. Even though this is peaks at red, there's still a lot of green and blue light in there. This would look like a whitish red, really. It's going to be much lower than that. I think 500 degrees or something less than 1000 degrees would make a metal ball glow red. And instead of just looking and observing the light directly from this object, there will be walls inside the box so that the light couldn't be directly observed. Instead, the whole box heats up due to the heat of this object, and once it all reaches the same temperature, then the light escapes. They measure that light, they graph the intensity of light depending on the wavelength that they get, and they get some kind of graph looking like this, where your red light is probably around here for this particular object, and based on this graph, they could measure very, very accurately what the temperature of this object is. So they're relating two things. They're relating temperature in Kelvin to wavelengths of light and the intensity of those wavelengths. And they did this for a whole bunch of objects of all different temperatures to work out what the mathematical relationship between these things were. This is where we get Wien's law. This is a relationship between wavelength and temperature. Max meaning the maximum intensity. So for this 500 degrees Kelvin, it would be this particular wavelength, right? The one there with the maximum intensity. Or for this one, it'd be this wavelength here, or for this one, it'd be this wavelength here, okay? The one at the very peak. For this one, it'd be this wavelength here. For this object, probably in the infrared or microwaves would be its peak intensity. It's a very simple equation to use. In fact, the way he wrote it was that the peak wavelength times the temperature in Kelvin is equal to a constant. And you can find this constant, it's in your formula sheet, in your data sheet. It's right at the bottom. Wien's displacement constant B, 2.898 times 10 to the negative 3 meters times degrees Kelvin. So it's these because it is the wavelength in meters times the degrees in Kelvin. Don't get it degrees in centigrade. Okay, so this was the experimental evidence. They didn't have any model or reason to say why this was happening. They just said, yep, these two things are clearly related in black bodies, temperature and wavelength, they're related. And we've got some mathematical equation which is pretty good at approximating at least one point of the curve. It couldn't describe the whole curve. Enter Planck. He created a much more sophisticated mathematical model, which included this little bit here. And his mathematical model had an assumption which hadn't been made before. His assumption was that the light coming out of the black body, that light has to be quantized. The light comes out in pieces, in particles that can't be divided. Okay, the smallest one possible being some multiple of a new constant called Planck's constant. And so this equation here describes the size or describes one piece of light. It says the energy of one chunk of light is equal to the frequency of that light, or its wavelength, because those two are in inverse, the frequency times some constant. And this constant again is on here somewhere. Surely it is. It's a very important one. Planck's constant H, 6.626 times 10 to the negative 34 joule seconds. Okay, seconds because frequency is in hertz, which is number per second, and energy is in joules. So by making this assumption, his mathematical model could exactly predict the shape of this curve, much more exact than my drawing of it. Exactly predict it rather than just predicting one little point. But also this assumption, it was a mathematical trick to him. He couldn't explain why light would come in little chunks. It turns out that this was a very important assumption because what he didn't know is that light actually is always quantized. It always comes in small packets that can be described by his E equals HF equation. And this was the beginning of quantum physics.